Yeah. Okay, you look a bit tired, right? Okay, so, well, this is my last class, and uh, we're going to do something a little bit different today. So before, what I want to do today is not so much teach you new stuff. Okay, so this is, I don't know, we are tired, and there was nothing I was really excited to teach you today. Well, with the time we have left, right? So instead, I'm going to show you some of the stuff that that we did, right? So me, Roberto, and a lot of other people did during COVID, and show you a few examples, okay? So that, and I think this also leads to some, so actually to several interesting discussions, right? That are, I think, are useful to. You know, stuff that is useful to think about, right? So more like life, universe, your role in it, your place in it, and so on, right? So, okay. So before I start, just let me ask if you know, because yesterday I think it was a little bit bleak in terms of results, right? So like everything we tried to do was was failing, right? So after thinking a little bit about the stuff we discussed, do you have comments, questions, stuff you want to ask about it, or comments, or yeah? No? Okay, so I'll start presenting something that is kind of the, I don't know, maybe best work we did. I don't know if Roberto would agree with that, but probably yes, right? So, but probably the best work we did during the at least the one we published, right? So I'll talk about this a little bit later, like the difference between the value you give to something versus what you publish actually, right? So, so this is something that we done at the beginning of 2021. Okay, so and this is actually a very large elaboration. I'll talk a lot more about this later, right? About the Observatório Covid-19 BR. Okay. And but the honest, I don't know if you well, all of you remember the pandemic very well, I hope, right? But then I don't know if you remember in detail what happened when exactly, because I don't know, maybe by now it's all kind of a blur. I don't know, right? Yeah. So it's like several years that are just kind of, well, yeah. Okay. So we are at the end of 2020. Okay, end of 2020. And there's a lot of discussion at this time about, well, by September, October, there are several places that are reopening in 2020, okay, because the pandemic had reduced a lot already in many places, like in Europe and several places in Brazil as well, and so on. And there was this whole discussion because we didn't know much about the disease yet, right? We thought well, some people thought we knew a lot of stuff about the disease, but actually we didn't know very much yet, right? So one of the big discussions was, is it possible to get reinfected by COVID? Yeah, of course, today this is quite obvious, right? Yeah, but back in 2020, a lot of people believed that the answer is that you got immunity for COVID, yeah, permanent immunity, right? And this would allow us to reopen more or less quickly in places that had already seen a lot of infection. Remember that this is before vaccines, okay? There were no vaccines in September 2020, right? So there was already some developments, okay, but no vaccines, no rollout of vaccinations yet, right? And this is time series for hospitalization cases in Manaus, okay, Manaus. That was one of the places that had the largest number of cases, largest incidence in Brazil. And there was this very, very famous paper, not by us, right, so from people we know, of that estimated that 3/4 or 75% of the people in Manaus had already got the disease by, I don't remember exactly when, I think it was by September or something like that. And this led to people thinking that, well, Manaus is safe now. Yeah, because, you know, 3/4 of people have already gotten the disease, they're immune, and, you know, we already knew estimates of R0 for COVID. It was, I think, about 2.5. So Manaus is safe now, yeah? Okay, and people were starting to reopen and stuff and so on, right? So what is the issue, right? So reinfection at this point was really hard to detect, right? Why? Because think about it for a moment from the clinical perspective, right? So you are trying to detect reinfection, but people that get the disease, sometimes they go back into the hospital and you don't know if it is the same disease, the same, just a new boot of the same virus that is still in the system or with the person, or if it is actually a new infection. It's really hard to separate reinfection from a kind of relapse or a worsening of symptoms, you know? Yeah, and also since your surveillance system for mild cases is really, really bad, right? So we didn't have a good surveillance for mild cases. We only had kind of good, right? Not great, but, you know, good enough surveillance for hospitalization cases, right? So in order to see a real case of reinfection, we had to look into the database for people that got hospitalized twice at 2 very different moments in time, like months apart, to be sure that this is not the same case, you know? But, you know, we were only a few months into the pandemic, right? So this is almost impossible to see by definition, yeah, you see? So we couldn't know much about reinfection by then, okay? So what happened, okay? By end of the year, end of 2020, there was this huge increase of cases in Manaus, okay, in Manaus. So we see that, where is the pointer when we need it? Yeah, here it is. So we have this first wave here that was already quite big, and then after elections we had this reopening here, okay, and just after the reopening it looked like nothing much was going on, and then by November we start getting increasing cases very, very quickly, and then December and January it was kind of tragic, okay, so there was a complete collapse, a lot of people dying because of lack of treatment and so on and so on, okay? So the question then is that, okay, later on we found out that this is, later on I mean by January, okay? By January we learned that this is actually a new variant, okay? So this is, I think this is one of, I think this was the second variant, or maybe third. Yeah, gamma means that it should be third, right? Okay, but actually it was kind of, all of them were really close in time, okay? So that was the gamma variant, right? So at the time it was called P1, okay? There was this nomenclature for alpha, beta, gamma came later, okay? It was the P1. And then the question is, okay, so what's going on here? So how is it possible that after having 3/4 of the population already infected, we can have this peak again? So the most obvious solution for this is, well, the first paper that I showed you was just wrong, okay? Because they didn't do that from counting cases, okay? This is just hospitalizations only, okay? So this is, if you just count hospitalizations, it's a tiny amount of cases, okay? So they had to infer from data collected from blood samples in, I think it's blood donors and so on. They inferred the total number of cases, and many people didn't believe those results, okay? They didn't believe those results. So this is one explanation, right? That number of 3/4 is just completely wrong, and this is just another epidemic, okay? And the second explanation is, okay, we may have a lot of reinfections going on. So this new variant is infecting people that had already gotten the disease, okay? Well, so what did we set out to do, right? So at the time, we were really, actually, the motivation for this is, well, this is happening right now in Manaus, okay? And this is beginning January, or mid-January, and we want, because of course it's going to spread, okay? If this is a new variant, and of course this is going to spread to the rest of the country, yeah? Yeah, you cannot really isolate Manaus from the rest of the country, okay? It's not possible, okay? So for us, it's going to spread. So we were interested in seeing, well, what is going to be the impact of this, okay? Is it the case, because Manaus is a very peculiar place, right? So is it the case that because Manaus has already relaxed it too much in terms of social distancing restrictions, or is it because of, you know, the health system in Manaus, the hospital system is kind of fragile, it's less well-structured than other places and so on. You know, we had to understand the impact of this in the rest of the country as well, okay? And for that, what do? We try to build a model for that. But to build a model, you need what? You need to know parameters, okay? And how do you figure out parameters, right? So what is the main stuff that is going to be important to know the impact in other places? If transmission is higher, and if it is possible to have reinfections, okay? And of course, you have to take into account here that maybe what we can have not full immunity, but we can have partial immunity, yeah? Maybe you are less prone to getting the disease if you had been infected before, okay? So we may have partial immunity, okay? So what do? Then we build a model with 3 strains, 2 variants, okay? Now we have the original one, the wild one, and the new P1 variant, okay? And what are we going to suppose? They have different transmissibilities. P1 has a probability of reinfection of people recovered from the original variant, okay? Do we have to assume the other way around? Like the original can reinfect someone that got P1? We might, but does that help? Because most of the people here, the new circulating variant is P1, so the cases in the other direction don't matter for this, okay? So we just assume that P1 reinfects people that got the original one, and we don't care about the other direction, okay? And finally, we may also introduce different pathogenicity, like changes in the hospitalization rate. So this is infection hospitalization rate. This is actually funny. It's called a rate, but there's no dimension of time. It's just a ratio. It's the number of people hospitalized divided by total number of infections, right? So it's the chance of being hospitalized if you get infected, okay? And yeah, this is also a possibility. Maybe the second wave here is not so bad. It's just that it is much more severe. So a much higher proportion of the cases are going to the hospital, yeah? So this is a first way to explain this last wave here, okay? Yeah. So you see that the model is able to explain not explain, but I had told you 3 different explanations for the second wave, and the model can just describe all of them, yeah? Okay, they are going to yield. It's going to yield different parameters for each of those different explanations, okay? Okay, so now model structure. Okay, so essentially we are going to need to use some kind of SIR, but actually for respiratory diseases, okay, I have shown you yesterday, right? SIR models, they're nice, but if you want to fit data, you need incubation period, okay? This is not obvious at first, but every model that you want to fit to data, you will need to take into account incubation period, okay? Because this is important to fit models, okay? Otherwise, you cannot get a good fit in terms of the growth and decrease of the growth curves, okay? Of the epidemic curves. Okay. And the nice thing is that SCIR is the same number of parameters because number of free parameters, yeah, because you know the incubation time, right? So it doesn't, yeah, you can be happy that way, right? And finally, we also need to include severity classes, right? Because it's not so much about the transmission, especially because by then all the schools were closed, so we didn't have that much heterogeneity in terms of, I don't know, children having such higher onset rates than adults and so on, because everyone was at home, okay? But the thing is that hospitalization, since what we are going to use is hospitalization data, okay? We don't have mild AIDS, okay? Only hospitalization data, then we need to take into account that the number of elderly people that is, or the rate of elderly people that are going to the hospital is higher than for younger people, yeah? So we also take into account some age structure into this model. We need asymptomatic infections by then. This is something that was kind of established by then, okay? Parameters were really wild around, but this was already well established. And we may also want to eventually compare to number of deaths. And we ended up not doing that, but we could, right? We would. So okay, age structure. Okay, so this is what I already commented, right? So we don't want to. It's not so much an issue of contents, but an issue of outcomes in terms of severity of hospitalization. So we did a very simple stuff that is only 3 classes. Okay, only less than 20, then adults 20 to 60, and then elderly people 60 plus. Okay. Okay, so this is our model diagram, okay? I don't know if this is much larger than what you have been doing. Probably it's about the same, I don't know. All right, but it's not, this is what our simple model, okay? Or not as simple as the one you learn, but it's not yet a full-blown model with, I don't know, hundreds of equations and so on, okay? So this is susceptibles, like susceptibles to never got infected by any disease whatsoever, by any COVID, and this would be an SEIR model for the original, the wild variant, okay? And now after the exposure time here, the incubation period, you have a division here where people can have mild disease, asymptomatic, or hospitalized, okay, severe cases, and among the severe cases, a proportion recovers, a proportion dies, okay? And the thing here is, for the second variant, this is exactly a copy of this, okay, down here. It's exactly a copy, with one big difference, okay? The one big difference is that people that are recovered from the wild variant, they can be reinfected by the new variant. Yeah? So this is the arrow here that makes all the difference. Okay? Yeah, the reinfection process. Okay? And what do we assume here? We assume that this beta, the new variant here, there's a beta that is different from the original one. Okay? And we assume that people that have already got the infection, they have a reduced probability or reduces susceptibility to the new variant, okay? So there are these 2 parameters here, beta 2 and PR here, okay? So this is transmissibility of the new virus, and this is probability or relative infection rate of people totally naive versus immune to the wild variant, okay? And finally, also we change it, remember that we also change the hospitalization rate, okay? Hospitalization rate is the sigma here, okay? Sigma 1 and sigma 2, okay? And pretty much all the other parameters are the same, yeah? Okay, so with that, okay? So far so good, people. Questions? Or questions not just in terms of what is written here, but maybe you're thinking, well, why didn't you include such and such? I don't know. Or yes, here. Hmm? You said yesterday that take into account that when you have Mm-hmm.
you can go to the exponential, the Gaussian distributed.
Well, what I said yesterday is that least squares. I'm going I'm going to comment more on fitting in a moment. Yeah. Okay. Okay. So your question.
About the gamma parameters, the
Mm-hmm.
rate with which the exposed individuals become infected.
Mm-hmm.
That parameter will appear only in the equation of the exposed. It will not in another.
Ah. Okay. You mean this arrow here, or not?
No, the one at the right, that one.
This.
No,
This.
no.
No. Expose it to. This is the compartment. So which arrow? This or that? This one. Okay.
That parameter only appears in the equation of the exposed. It does not appears in the, I assume, in the equation of the infected compartments, right? Because
No, but this is kind of incubation period and then divided into the 3 classes. Yeah, this is the same. I think gamma 1 and gamma 2 are the same, actually.
yeah, what I mean is, in the typical models, gamma will be the rate with which the exposed become infected. So it
Yeah.
appears in the exposed equation and in the infected equation.
Yeah.
But in this case, the gamma parameter appears in the equation of the infected compartments, or is only, I don't know, maybe it's just the rate with which the exposed leaves that compartment, but
Yeah. This is the rate with which they leave this compartment and reach those compartments. You see, because this is a rate, this has dimension of time, and actually gamma 1 and gamma 2 are the same, and these here are just probabilities, just proportions, right? This sigma and this alpha here, these are all just probabilities. So they don't have, they sum to 1, the 3 of them. Yeah? Is it clear? Yes. You have to talk really loud now.
how do you set an initial condition to get first pick of the first?
Well, good question, good question. I'll get to that. Yeah.
I find it difficult to know how to compare.
Yeah, okay, so this is going to be a bit hard, but then, okay, so this is about fitting also, right? So how do you set the initial conditions? Okay, just to maybe clarify Thomas' question, so let me, I think at the end we have the equations. Yeah, okay, so these are the equations, right? So for E here, you see there are the lambda 2 from naive individuals and lambda 2 times PR from over individuals from strain 1. And you have here the E2 over gamma 2, and then you have E2 over gamma 2 for A, I, and H, multiplied by some probability. Does that answer your question? Yeah? Okay. Okay, so let me go back there. Okay. So now, a lot of parameters, okay, a lot of parameters. But then many of them we already had, okay? So we actually spent the whole 2020 fitting models as well, right? So we had many of them. So we had fatality rates from people hospitalized from the CVAP drip that Marcelo told you about the other day. We had some measures of, this was kind of hard, but we had some measures of rate of hospitalization from infections by age. Of course, we had age structure from IBGE. We had these contact matrices from plane that I told you about on Tuesday, yeah? On Tuesday. And also we had the data from hospitalizations, okay? Yeah? So, okay. And this is, I think this is related to your question. So how do we set initial conditions? Yeah? How do we set initial conditions? So the thing is, you have hospitalizations in the previous week, yeah? Like we are starting, I don't know, at sometime in October, for instance, okay? We know hospitalization at the at the starting week, okay? And from the model, okay, from the model, you can, there are a few different ways of doing this, but since, you see, since this is, since these are just proportions, okay, these are proportions that you'll hear here and here, then, and these rates here are pretty similar. These rates of leaving those classes are pretty similar, okay? The difference between recovering from mild cases and hospitalized cases is not so, there is some difference, but it's very small. So actually the number of infectious and asymptomatic are just kind of proportional to hospitalizations, okay? I think you can do some simple calculation. You have to do some assumptions, but you can do some calculation to estimate from that, from the sum of total number of infectious, the number of exposed as well in the beginning, okay? What you don't have, actually, what you don't have is what are the remaining number of susceptible individuals. You don't know how many, just from hospitalization data on that week, you don't know how many of them are still here and how many are already recovered, yeah? That you don't know, okay? But the middle here, you do know, okay? And of course, the part down here, we initially set to a very small number, okay? But this also we have to fit, okay? Is that more or less your question? Or? Yeah. So this is how you set the initial condition. So from the data, you can more or less get everything here, and the initial number of susceptibles and the initial number of the new variant, you will need to fit data, okay? Question?
Why there is a transition from infected to dead?
Well, infections go to death via, here, you see, so age. So this is only mild cases, right? So people that are mild case, you assume that everyone that is going to die are severe case before dying, right? So they are hospitalized, yeah? Yeah, yeah, yeah.
The model is not considering the people that died
At home, without going to the hospital. Yeah, but this number is actually pretty small, right? So it wasn't so small by mid-January, but even then it's small enough to ignore, right? So we have data on this, and it's not like making a huge difference, okay? Okay, more questions? Okay. Nice. So far, so the interesting. I don't know, this kind of real scenario, real world scenario. Okay, so it's kind of funny because like we like to do simple. I know that people look at this and maybe think this is not so simple. But this is a simple model, believe me. And it was simple because also we wanted to do this very quickly. Very quickly. Like everything else in pandemic, there was a big urgency, okay? So we wanted to do stuff like fast and even if it's a little bit rough, okay? Okay, so what else can we use to fit the data, right? So we have new cases per week, and now we had to now catch this data, right? Because we're doing this in January, and the data from November and December is already, is still very much incomplete, okay? And from January, it's, right? So so we have this black dots here that ends from CVAP drip, okay? And we also have something, and this is where stuff is kind of difficult, okay? That how do you fit something? You have 3 strains, right? But you only have total number of cases. Total number of cases. The total number of cases is the sum of the 3 strains together, okay? How can you, if you don't have any information at all about the relative frequency of the 3 strains, then it's impossible to fit this model, okay? It's impossible, okay? But fortunately, we had some data from Fiocruz and from the group of, from Faria et al., that is actually the group of Esther Sabino that published the 2 authors paper that 2 authors infection attack rates from the previous slide, okay? So we had this, and these are the data that I'm talking about, is this stuff here, okay? So the dots are the measurements of frequency of the new variant, okay? So it's beginning at 0 here in November, and it goes up up to close to 90% by start of January. Yeah. Okay. So you see that P1 really increases very quickly. It becomes dominant very quickly. Okay. And these are error bars. Okay. Because this is actually a very few number of individuals sampled. Right. So the error bars for these frequencies are actually very large. Okay. Okay. So what are we going to fit? So we are going to fit the our main parameters that we're interested in is how much more transmissible the new variant is compared to the original one, the wild one, and what is the reinfection probability? How or in the other way, right? So how strong is the partial immunity that you get from the original variant? Okay, is it full or is it just very small? Or, yeah. Okay, and then there are other parameters that we have to fit as well because we don't have data. So these are parameters that in principle, if we could get from data, it would be great, but we don't have, right? So we have to fit them. The first one is the initial condition of susceptibles, okay? How many people are already recovered? How many people are still naive to any COVID virus, okay? So the seroprevalence at the time of the emergence of P1, okay? So the second one is what is the frequency of P1 at the very beginning? Okay, so the thing is, this is kind of weird, right? Because when we do an OGE model, right? So we usually think of, well, I don't know, P1 started, I don't know, in November, and then you go and say one infectious individual at the 1st of November, but we don't know if that's the correct date. Yeah, you don't know. There's no way to know. Actually, right? It's hard, right? So there's an uncertainty in the date, okay? There's uncertainty in the date. So what do you do instead is that you fix the date that you want by convenience or whatever, okay? Of course, it cannot be in the middle by January, okay? It has to be close to the beginning, but you fix the date that you want to begin the simulations, and then you allow the initial number of infected individuals be kind of free, you know, you fit it also as a parameter. It means that if by 1st of November, my fitted model has already one infected individual, it means that, okay, the start date was really 1st of November. If I get initial condition that is, I don't know, several individuals, it means that the initial case is a little bit older. And if I get a number that is smaller than 1, then it means that actually the start date is later than 1st of November. Is it? Yeah? Okay, so this is one way to think about this. And fit this because you have an uncertainty in time for very small numbers. An uncertainty in time becomes an uncertainty just in the initial condition. Okay? Yeah? Okay, nice. And finally, you also have to take into account the original variant's transmission rate, right? Because this is, even though we know R0 for the wild variant, real world is messy, right? Because, well, you had social distancing, you have mass use, you have schools closed, so you know R0, but you don't know the actual R at the RT at that moment, you know? That depends on a whole lot of social behavior, you see? Yeah? So you actually have to fit the transmission rate as well. So you have to fit beta for the original variant as well, okay? So this, how many parameters we have here? We have 5 parameters, okay? So this already puts us into hot water, yeah? Okay, so 5 parameters to fit, okay? Okay, so here we didn't use least squares, we used it, because here we have kind of a complex situation, right? Because we are fitting 2 different kinds of data at the same time, okay? We are fitting this time series here in black, okay? And we also fitting frequency of P1 from 2 different data sources, okay? This from Fioruz and this from Faria et al., okay? So we are fitting different sources of data, so we essentially build a model, like a probabilistic model, for the errors that the model makes with respect to this. And this leads us to to a likelihood function, okay, a likelihood function. Again, this is still very simplistic in terms of not considering noise from process, okay, so this is, but then, as I told you, we try to do this like in 1 week, okay, so yeah, so this is rough, but works, okay, but when we have 5 parameters, what happens is that we had a lot of local maxima, okay, a lot of problems fitting this model because you have lots and lots of local maxima, right? So if you start if you just say, fit this for me, and you start with a certain initial condition for the parameters, it goes to 1 peak. If you start from another point, it goes to another peak. So we had to run like a full-blown computational process of finding all of the local peaks and then finding the global optima. So this is the 2 parameters that we are most interested in. But we also have here in the columns, I guess, this is the initial number of recovered individual in each column, and in each line is the initial condition of P1, okay, for different ranges here, okay. And in color is the negative likelihood. Okay? So this is the one that we want to optimize. Okay? So this is actually conceptually simple, computationally a little bit complicated. Okay, yeah. So I don't go into much detail of how to do this and so on, but yeah, but conceptually makes sense. Yeah, it's pretty much what we discussed yesterday. Okay, but this is now a likelihood function, not least squares, because we use I think binomial errors for the probabilities, and I think it wasn't Gaussian, it was negative binomial, I guess, for the number of hospitalizations. I guess that's what that is. Okay. Oh, it's written here. Okay, so a Poisson distribution for yeah, and binomial for the P1 samples. Okay, this is why you need to write down stuff in your slides. Yeah. Okay. Okay. So. And this is the best fit, okay? So this is the best fit. So the best fit is, this is comparing, so this line here is what you get from the model, okay? Here and here. So, so we take the number of cases, I think these hospitalized cases, and we see the proportion of P1, assuming that the sampling was random, right? So this is the proportion of P1 among the hospitalized cases here for each of those weeks, and here for each of those months, okay, because Fioru's data was by month. And here you see that we can plot 2 curves, one for hospitalizations of the original variant in blue, and one for hospitalizations of the new variant, yeah? And the sum of those 2 curves is this black curve over here, yeah? Okay? And it's reasonably good fit, yeah? Okay? And what we learn from this, what do we learn from this? We learned that the new, with the best fit, the new variant is about 2.5 times more transmissible than the original one. And we have a relative force of reinfection that is that probability of error of only 3%. It means that if you got the wild strain, you are 97% protected. Yeah, so there's a strong, actually, there's a quite strong partial immunity. Yeah, even then, the transmissibility was so high that of the new cases here, 28% of them were new infections, were reinfections. Yeah, 28% of the infections, the total new infections in this period here, came from reinfections, even for these people had a much lower risk of getting infected. They are like 32 times less likely to get infected. Yeah? So this is kind of interesting, right? Because it's something that is not obvious at all, right? Because you think, well, if I told you that the partial immunity is like 97%, you would kind of rule out reinfections as a main explaining variable. But actually, the infection rate is so much higher that this is important. Yeah.
That's where human behavior takes into account, right? Because maybe because of people that already had been infected with the first variant thought, oh, okay, I have immunity, okay, go out. So more than a totally susceptible person, and that would be why the approach is so high.
Mm, I don't think so, right? Because this doesn't consider difference in behavior between those classes, right? So this means that this number, this 3% here, includes the fact that they can behaving differently. You see, like for instance, suppose that this partial immunity effect was only 50% from a biological point of view, but they were twice as likely to go out and party, I don't know. Then the observed value here wouldn't be 50%, it would be like 20%. You see, because this is already compounding everything together here. You see? So maybe the actual biological protection is even higher than 97%, but by behavioral processes, they are more likely to get exposed to the virus. Yeah? Okay? Okay, and then there are other parameters here. One nice thing here is that our initial prevalence of the disease is pretty close to 2 orders, right? So at least from our point of view, that paper, and we actually didn't assume this, right? So we fitted this, like this is a range you cannot see from here, right? But this is, yeah, this is starting at 30%, okay? So this is starting at 30% up to 90%, okay? So we didn't assume that it was 75%, but it came out pretty much like that, okay? So this is a happy situation after, so yeah, okay, happy situation. We got back from the fitting something that we were not completely sure about it, but not so surprising, okay? The initial growth rate, this is the growth rate of the initial variant, of the original variant, and the initial frequency of P1 at the beginning of November. So it means this number here is, you see, is quite smaller than 1. So it means that actually P1, even though it may originated earlier, it only began to spread really quickly after 1st of November, okay? Yeah? Okay, so questions? Nice? Nice. Now we have to do some analysis here because I told you that you can increase severity, right? But we did this and it didn't change much the results if we include an increase in severity. And we were also worried that hospitalization data after hostile collapse in mid-January would be really bad, right? So we tried to fit the model again, throwing away hospitalization data from mid-January onwards, okay? So not going up to the end of the month. But this also didn't change much except for this guy here, and this is kind of weird, right? So, okay, but for transmissibility, this becomes larger, okay? Larger transmissibility. So just to make a point here, one thing that makes us very happy about this, actually, is that the same group later on, they estimated reinfections using, again, blood donor samples and so on. The number that they got for reinfections, the people that got infected twice, was very close to this, okay? So it's kind of, I don't know, maybe a happy coincidence or maybe, you know, things converged quite well for this paper here, okay? Okay, so limitations, of course, we have a small sample size for frequency of P1, you have possibly underestimation of hospitalizations, but in many of those cases, this is the kind of limitation that you always have and that you're not so sure in which direction this would pull the results, you know, so yeah, you can know that, okay? And also we didn't consider waning immunity, okay, that maybe these days we could, okay, so like people losing immunity, but by this time, it was in the very beginning of the pandemic, like, so most people in Manaus was first infected by between April and May, right? So it wasn't so much time after that yet, right? So maybe waning immunity wasn't so important at that time, okay? Okay, so these are conclusions, pretty much what I told you about. There's this paper here. This is not a Nature paper, right? So this is a Nature group paper, right? So this is, I think, Communications in Medicine, right? It's not Nature, okay? And now I want to talk to you a little bit about how this comes about, okay? So how, so this is a huge group of people, right? So many people that help with this, but this came from, so I think I pretty much finished with what I want to talk about this model here now, so yeah. I want to talk a little bit more about the work of Observatorio, okay? But I want to know if you have questions or comments and so on about what I just presented, okay? So this is it, yeah? Questions, comments? Yeah, so it's one case where actually this even raw fitting can work, okay? It's quite a lot of work, but sometimes it yields useful results, okay? And with those results, what we did with that, right? So we built a model for the rest of the country. So we had some idea of seroprevalence in other places, in other states, and so on and so on. And we run some simulations, and by beginning February, we were predicting catastrophe all over the country, and it did come, right? So there was a catastrophe all over the country, okay? So it was pretty much the history of P1, right? So it could be worse, right? But this is not something that we published, okay? So this is something that we circulated among a lot of people that we know, but, you know, kind of, yeah, I'll talk about this in a moment, but still, questions about this? Questions? Okay, so let me talk a little bit about what we were doing at that time, okay? So let me go back here in a moment. So, for instance, for this work here, our original intent was just finding parameters to estimate the impact of P1, of the gamma variant, in the rest of the country. And this goal is something that we did, and we talked to several people about it, and not people from public health and so on. But it's something that we never published. Yeah, it's not. There's no paper on what is going to be the impact of P1 on the rest of Brazil, because by the time you write such a paper, P1 is already spread over the whole. The stuff already happened. Okay, so this is real-time stuff. If your goal is to do this kind of thing, you have to forego a bit your goals in terms of traditional academic publishing. Yeah, there is a trade-off, okay? And this is very, very important to mention, okay? So we did a lot of stuff that is not in my CV, is not in my, like if you look at my CV, there's only, participated in Observatorio, and not much detail, because a lot of stuff you do that you never publish, you only present it into restricted circles or to specific people, and it's not that it's not important. Sometimes it's more important than your published papers, you know, because most papers are not very much read, you know, yeah? You do know that, right? So most papers, it's not like you're going to publish this and everyone in the world is going to read it, okay? Yeah? Even papers such as this is quite well cited and so on. But even this is not like it's going to change the world, you know? So sometimes you have to balance a bit your desire for academic recognition and publishing papers and so on with, well, what is useful to do right now, okay? I think of it was an extreme case where everyone was really focused on helping, on contributing to the science behind the disease, to the science on the disease, to contribute to public health. But in normal times, this is also relevant. It's not so extreme. Like it's not like I have to produce this in 1 week to to get results like this. Okay, but even then, this is relevant. Okay, so. Yeah, so let me go back a little bit. Okay, so Observatorio, and now I don't know how much time I have. Yeah, I have. So I don't know. Do you like to hearing stories? I don't know. Yeah, let me talk about some stories, okay? So, yeah, because, uh, you know, I don't know how to present this as an introduction, methods, and conclusion. You know, stuff just, it's happening, okay? So how do you end up with a huge group of people? And let me go back here and show you. The web page is still up in the air, okay? Is still available here, right? So, and the group later on became like much more people, okay? So a lot of people working together on this, and there was a huge discussion group and so on, right? But and now the web page is really like all fancy with, you know, but I open here, where is it? Yeah, where is it? Yeah, what, you know Wayback Machine, right? Wayback Machine, this is Internet Archive. You can save web pages here, and it remembers how the page was at that particular time. And this is what it looked like, this our web page on March 23, 2020. You see, so 1 week after school closures, university closures all over Brazil, okay? And this is like, we just had some plots for very simple analysis. You see here the duplication time of the disease, the calculation of the RT that Roberto just talked about. We use this kind of method to calculate the reproduction rate of the disease. We had some initial analysis from another group that was looking at networks and also networks over Brazil and so on, this kind of stuff, from flights and so on, okay? And we even have some, this is daily data, okay? So this is, we were kind of extrapolating new cases for next week and this kind of stuff, right? So this is very beginning. And at the very, very beginning is like, you know, you want to do something, and then our longtime collaborator, Paulo Inácio, wrote some scripts that took this public data and fitted some very simple exponential models and so on to see growth rates. He writes to Roberto, and then Roberto writes to me, and then we had already some experience, and then we say, well, why are we publishing our website again? Like, and we said, okay, yes, let's do this, okay? And then we start talking to other people like you, like people that have been in schools before and so on, and then a lot of people wanted to work on this, okay? And then suddenly we had dozens of people wanted to work on something, and we were trying to coordinate this over Zoom and over whatever, and this is how Observatory started. We wanted to do analysis of data and models and so on together, and trying to digest this and put it into a public format that is consumable by the public, okay? So this is website, even for it looks pretty technical, okay? Because we are not like great at communication, right? So, but like we wanted to provide and good information, okay? Good information, like good analysis that can help public health experts or the general public to understand what's going on and to, you know, have more, because if you're not an expert, it's really hard to know what's going on with a disease, okay? Because if you have read any media reports on diseases, right, it's actually pretty unhelpful if you have a little bit more of a technical eye, right? So either the reports are only like, well, this guy here, such and such a name, had this disease like this and this, so it's just a report of the specific case, and when they start talking about numbers, things go badly wrong. Okay, so just last week we were laughing because people didn't learn anything about the pandemic, right? Because people were saying, okay, but now dengue is over. And we are, oh no, like they just saw, and I just opened the InfoDengue case here, the InfoDengue website here, just to show you what I'm talking about. So this is dengue in São Paulo, right? And this is black line is reported cases, but the the vertical lines here are estimated cases. So it's not, people are looking at the black curve here and saying dengue is over, right? So no, it's not over. Like it's, you have to take into account delaying reporting and so on, right? And you know, so this kind of stuff, okay? So it's still very bad, okay? It's still very bad up to this day, okay? So, so this is something that we wanted to do, and pretty much just, I guess, 1 or 2 weeks later, right? So so we were at the time, right? A bunch of mathematicians, physicists, and also ecologists, right? Because they all usually had a lot more ecologists and biologists than public health people, okay? We didn't know so much people from public health, okay? But then Maria Melli wrote to Roberto, right? I don't know, maybe 1 or 2 weeks later. Yeah. And she was working, she was working with the Municipal Secretary of Health in São Paulo. And also, but you know, she's very, very, you know, she's a hub in the UNTAD network of public health epidemiologists in the academic side, right? So actually, and then we started to work a lot of public health people as well, right? So and working also with like, I don't know if you remember this phase from the pandemic, right? In the very beginning, where everyone was trying to do something, but few people actually have much experience doing this. Okay, so there are a bunch of really bad stuff being published, okay? Like, I don't know, people that fit polynomial to epidemic curve, like, but a third-degree polynomial that goes like this, and then, so if you stop here, it's fine. If you go 1 week later, you have negative cases, okay? So, not right? So, but of course, if you stop just here, you see that it is starting to fall. you see, so it's, and then we started doing a lot of work of communicating this, okay? So we started to talk to a lot of journalists, because pretty soon journalists, they need sources, okay? They need sources. And then when you become recognized as a source, then you have more influence in terms of which public you can reach, okay? So once people recognize that we as a group was a good source for information, a lot of journalists started to run stuff by us, and then we can point to, okay, no, this is garbage, or this, we cannot say this with any confidence, or, oh, this is okay, or this is, yeah, we can start to influence public opinion, or how stuff is reported, using a good scientific evidence, you know. So so this is not this is really a full-time job, okay? Because sometimes I think Roberto was the one that taught a lot more to the press than I, right? So because it's a better communicator, right? So I don't know. I think I had weeks where you were scheduling back-to-back interviews, right? With, yeah, so like yeah, so and yeah, there's this phase, like, right? And then in the very beginning, we were kind of trying out different things, and then we a lot of stuff that we know now, we learned it. We had to learn by force at the time, at the point in time. Okay, so like we didn't use to GeoFCVAP DRIP before, right? So we were doing epidemiological on static data, and then we were forced to learn how to do node-hashing, how to analyze data with large error bars because of uncertainty in node-hashing, because of uncertainty in many parameters. So a lot of stuff we really learned by doing, okay? You are kind of privileged that you don't have this burning thing, like you have to do this for tomorrow, and you are learning as you're doing and so on, right? But then that's how things go, right? So I have some, yeah, I want to go back to to the question of what. Let me just show you a little bit more of this, right? So something that, so we were doing this stuff with nowcasting, right? So of course here, this is the nowcasted region. This is already a long time, right? So so we had the nowcasting, we had a calculation of RT, okay, for different points in time and so on, this kind of stuff. But we also had a lot of analysis from well, after some time this just became very long, right? But a lot of analysis from models, analysis from other people that were writing together with us. We had even frequent questions and so on, right? So common terms and so on, and then a whole list of places where we had shown up in the media and so on. Okay, so but the thing is, this takes a lot of time, right? So keeping up a website that is updated at the very beginning, we were updating analysis every day. Later on, I think by June, we started doing weekly, but it's a lot of work, okay? So our first papers started coming out only by the end of 2021, okay? And but in 2020, we're only doing public-facing research, you see? So only doing stuff connected to working together with health secretaries of some municipalities, with some states, and providing background information for journalists and so on, you know. So and this is a choice, of course, but yeah, I think it's something that you have to think about, right? So am I doing something that is able to affect how people understand something, how people affect some disease, how people understand ways to mitigate disease, or how the public understands some questions, okay? And if you do this, you have to then start being more careful, because when you communicate with the public, is a completely new set of challenges for communication itself, okay? Because you have to be very explicit and and you have to simplify as much as you can what you're saying. You can no longer, because it's kind of safe to write for a technical public, okay? You write a jargon, you write using technical terms, you write using math, you build complicated plots, and you know that the public reading those papers, they are able to understand what you're doing, right? They may not understand, okay, of course, but they are able to understand what you're doing, right? But when you communicate with a journalist, you don't even have a plot most of the time, okay? You have to say stuff in very general terms, but taking care that the person understands what you're saying. Otherwise, what happens frequently is that you say something and then you read that the person understands did something completely different, okay? And then you start to think, okay, how what I said led to this conclusion that the person wrote in the paper. You see? So it's I don't have this would be another course, right? So public communication, but we are not doing this here, okay? But it's something that if you're going in this direction of being used on more of these public-facing issues, is a very good thing to get training on, okay? So it's my view, yeah, okay? Yeah, so I have other examples of more interesting stuff that we did, right? So we did stuff later on with vaccinations, okay? So modeling vaccination, we also modeling school reopening. I think with vaccination, it was quite nice, and then we got to, yeah, let me show this just quickly, okay? So this is a model for I won't present this and so on, but this is a model for vaccination where you have 1 and 2 doses, and then we are trying to answer the question of, well, how long, what is the best interval between doses in order to optimize this process and so on. Okay, this is a published paper, right? So you don't need to should take, you just look at the name of the paper, right? So you go there and it's, yeah. So, and this is quite nice. The other one that in theory was quite nice, but in practice it didn't help so much, was this model on school reopening, okay? So this was already end of 2021, beginning of 2022, and the vaccinations were rolling out and so on, were starting to roll out. And then we did a very complicated model with quarantine and isolation and contact tracing. It was, I think this is one of the most complicated models that we did in the whole this is all structured by age with 19 classes, and the rules are very complicated for quarantine, for contact tracing, and so on and so forth. But it ends up that this one we got completely ignored in terms of, because we ended up seeing that, well, if you have low incidence, it's okay to partially reopen schools, but if not, then not. But the reopening cannot be 100%, otherwise you'll have a strong surge in cases. We had a lot of nice conclusions from this. But you know, we couldn't, this is the kind of stuff that ended up being nice from a modeling perspective, but we wouldn't put it out there. You know, this had, I think, zero influence in what later went on, right? So people were just want to open, and it doesn't matter. We don't want to hear anything about the science behind this, and we are going to reopen on the second semester, and that's it, and whatever. You know, like no, we wouldn't convince journalists to write about this, and that's it, right? So it's just a published paper, okay? It's a nice model, published paper, and so on, but not so much in terms of public policy, okay? Okay, people, comments, questions, or, yeah, yes? Yeah.
Everyone who participated in this group, from the very beginning, they agreed they were not going to publish anything.
Yeah.
Just last year, they published a book telling what they were doing during the pandemic.
Yeah, it's something that we considered, but you know, it's a lot of work as well, right? So we were like, burnout is real, yeah. So burnout is real. So I think it was pretty much everyone burned out by 2022, end of 2022. We were not able to anything more than you know, keep going with what we already are doing, and that's it, right? So so we haven't got around to it, and I don't know if we will get around to it eventually. Probably not, right? But maybe, yeah. And also, some of the best stories, right? So that I'm not telling here. Some of the best stories about how it works, like when you are talking about public policy, is that you build relationships. Okay, so you build relationships with people that work on public service. Okay, so you build relationships with people that, and it's not like I know the secretary of or the minister or something. No, it's people that are hired. There are public services that are hired inside the secretaries of health. Okay, you build relationships with them. Okay, and then you get to help with public policy. Okay, so it's really something that. That is not because when you say public policy and so on, this looks very abstract. Okay, but in practice, it's not abstract. It's really a network of people. You see that you are talking to and exchanging information, exchanging ideas, and it's kind of hard to go into that detail without exposing a lot of people as well, because sometimes we had we had a lot of political interference as well, right? So, so at some point, for instance, our work on Secretary of Health of the city of São Paulo was closed down. Yeah, just closed down, you know, and
And at the very beginning, there was also the point that data was not available.
yeah.
That changed over the course of the epidemic. Now we have the data every week and so on. But at the very beginning, data was not available. So you had to work with a public health institution or the secretary for health of your town or of your state or whatever. They had the data. So, for instance,
Yeah.
the city of São Paulo, when they decided they didn't want the work group of modeling and so on, so they cut it, and we didn't have data.
Yeah.
Anymore.
Yeah. And yeah, there are a lot of spicier stories as well, right? But those I cannot talk about with, you know, with recording going on, okay? With public recording, okay? So there are a lot of stories, okay? But this is all very interesting, but it's not. I'm not going to write a book about it, okay? Okay. More questions. I don't know if you are satisfied with that answer, but yeah. More questions. Moments. I don't know, people, has this is a different thought, right? But has this been helpful somehow or interesting? Yeah? Okay. Yes.
Are based on differential equations. I want to know if your experience, there is the usefulness of agent-based modeling as well.
Okay, so we do differentiations because we like differentiations. Okay, so this is something that that is important to notice because it's not like, oh, if only differentiations are all that is important and so on. But it's the stuff that we know how to do well. Okay, so it's important that you, if you're going to do something, it's important that you have a good grasp of what you're doing. Okay, so and we don't have such a good grasp with agent-based modeling. Okay, so also it's harder to fit data. It's I don't know. I see a lot of drawbacks that someone that works with agent-based models don't see. Okay, yeah, they love agent-based models and they know how to work with them better. Okay, so. I didn't hear.
It's more like a personal thing.
Yes, like there, I can tell you stuff like reasons that are objective reasons. Okay, like it's not just that I don't like agent-based models. There are, I don't know, they are more computationally expensive. They usually have more parameters. They take longer to run, so on and so forth. But you know, besides the objective reasons, of course, there are the subjective reason that is probably stronger, right? That is, I like differential equations and I use it to work with them. Okay, so maybe the objective reasons are just a thin veneer over the subjective reasons. Yeah, yeah, because people have worked with agent-based models and that's okay. But you have to be able to do that well. Okay, to be able to fit parameters, to make models that are not agent-based models have a lot of small rules everywhere that you can change a little bit, and it looks like it doesn't make a lot of difference, but then it does. Okay, so it's more complicated. Okay, good enough. Yeah, it's something that we have worked. We didn't do that so much in COVID, but we have worked with before is stochastic differential equations, right? So taking differential equations and adding noise, and then you are able to fit models that take into account process noise. That we have worked before, but not here. Okay. More questions? No. Okay. So So, well, we stopped a little bit earlier today. Okay, people. So, thank you.